Welcome back to everybody. In this lecture, we will focus our attention on the problem of robots interacting with the environment. More in particular, we will focus on the problem of controlling the contact, so the exchanges forces between the robot and the environment, and the motion that the robot may have in contact with the environment. So we will not deal too much with modeling the geometry of the environment insofar that the modeling is needed in order to perform these tasks. We will see that the modeling part and the control part in this type of interaction tasks are strictly related one to each other. So while so far we have considered only robot in free motion, now we will see what are the characteristics of interacting physically with the environment. In particular, there are two ways in which the robot, mainly through its end effector, its tooling, may have a physical interaction with the environment. First, modifying the state of the environment. For instance, when the robot is doing a pick and place operation in which it moves an object from one part of its workspace to another part, from one place to another. There are a number of tasks in which the force exchange is of primary relevance. For instance, when we are assembling parts and we have to push one side of one object to another side of the object, make them surfaces sliding one with respect to the other. Or when we are doing mechanical operation involving, for instance, a surface finishing task of metallic object. The main difference between controlling the robot in free motion and controlling the interaction may be also assessed by the number and type of sensor that are being used. For instance, in this picture, we see a robot carrying a camera and doing an inspection task. For doing this task, the end effector, and the camera in particular, should follow a prescribed path with a given timing law. In order to execute this type of free motion task, we typically use position measurement at the joints through encoders, if needed also velocity information at the joint, typically obtained by numerical differentiation, and less common using tachometers. But we may also use other type of sensor, for instance vision by the camera, mounted eye in hand, or the end effector motion is driven by the scene viewed by a camera which is placed fixed in the environment, and so on. But essentially, the matter is a matter of controlling in time the position of the end effector, or equivalently the position of the joints once we transform through the inverse kinematic and inverse differential kinematic the desired motion in the Cartesian space. Whereas typical cases of robot-environment interaction, it's executing what is called usually compliant motion. Compliant motion in the sense that the end effector of the robot, which is the main point where the interaction occurs, should comply with the stiffness, or say the geometry and the stiffness of the environment. A typical task, assembly task, is what is called peg in hole. So a peg should enter a hole with very limited clearance. For doing those tasks, we certainly use and need the previous sensor for free motion control, in particular encoders, and sometimes also camera in the Cartesian space, but it is very convenient to have also a direct measure of the force exchange at the level of the end effector. And typically we do so by equipping the robot with a 6D force torque sensor mounted at the robot wrist. So the closest possible to the point of contact, although most of the time we cannot mount a force measuring device exactly at the contact, because otherwise we would either destroy the sensor or not having the tool in the right form and shape to execute its mechanical task. So when talking about robot compliance, usually we distinguish between two types of compliance, namely passive and active. Passive compliance is realized by adding some devices on the robot end effector which comply with the forces that are being exchanged when the end effector of the robot enters in contact with some workpiece. We usually talk about TCP, so tool center point, by characterizing the position of in the end effector frame, where the main exchange of contact forces and moments should be realized. So, for this type of passive compliance, so it's a way in which the robot continue to execute essentially a geometric plan with the trajectory, so with time in motion, without caring of the presence of these contacts. The contacts and the forces that arise at the contact are handled passively by these mechatronic devices. And we will see in a moment the main device that is being used for giving passive compliance to a robot is the use of a device which is called RCC, so Remote Center of Compliance. And we will see how this works and what are the pros and cons of such a solution. On the other hand, one can incorporate into the robot system some active compliance, which is typically a software-based characteristic. So it's a way in which you design control law so as the robot can react in a specific and desired way to the generalized forces or forces and torques that are being applied from the end effector, from the environment on the end effector, and in particular at the tool center point. And these forces are typically measured by a force torque sensor. Now, in this context, we will see that there are different ways in which this reaction, so the control law, can be designed. And by and large, we characterize three categories of control laws. Admittance control laws, stiffness or compliance control, and impedance control. In the first type, the forces, the contact forces that arise when the end effector is in contact with the environment are measured and translated into velocity commands. And this can be done at different levels, at the Cartesian level or at the joint level. The velocity commands are given then as reference to some low-level control loops which are designed or embedded at the joint level of the robot. Stiffness or compliance control, these two terms are used equivalently. In fact, one is the inverse of the other. If you have a stiff environment, has low compliance. If you have a low stiffness environment, it has a large compliance. In this case, the displacement of the tool center point with respect to some reference position will generate some force commands. Again, force commands are nominally generated at the end effector, but then they should be realized by proper command, torque command at the joint level. The third class of this type of active compliance are impedance control. In this case, there is no one-way direction between contact forces and displacement or velocities. But in fact, we try to match a desired interaction model which relates displacement of the contact point with respect to some reference position with contact forces that are being applied in the interaction. And we will see in more detail how these methods can be designed and their properties. There's another way of handling interaction, which is more geometrically oriented, in which we don't impose a compliance necessarily in some direction, but we separately control the interaction forces in direction where contact occurs, while controlling purely motion in the free direction of the Cartesian space where the end effector can freely move. And this is what underlies hybrid control methods. Hybrid in the sense that we are simultaneously controlling in different directions force or motion. And we will see more in detail this later. So with this picture, general picture in mind, we start looking at passive compliance, and in particular how an RCC device works. So from a viewpoint, from an external point of view, these RCC devices look like force torque sensors. So they have a cylindrical shape. One top plate is being fixed to the final flange of the end effector. The bottom plate will carry some tool. So it is mounted at the level of the end effector of a robot. It comes in different size, and of course each size has some range of value under which the device reacts with displacement to applied forces, and essentially the two plates are connected one to the other with flexible elements. So kind of springs or springs-like components which allow one plate to move relatively to the other. In particular, the bottom plate, which holds the tool, relative to the top plate, which is attached to the end effector of the robot. So the robot will continue moving as planned, so it will move the top plate in any direction. If a contact occurs, it occurs with a tool which is mounted, which is attached to the bottom plate of the RCC. So there could be a compression, there could be a tension, there could be a torsion around the approach axis. There could be some lateral angular displacement, which is also called cocking in the literature. So let's visualize with a couple of sequential figures what happens when a robot is trying to execute an assembly task while mounting a remote center of compliance device. So there is one point associated to the device, which is exactly the RCC point, which behaves in a very special way because of the mechanical construction of the device. So imagine on top of the figure a robot holding the RCC, and below the RCC there's a gripper, and the gripper is firmly holding a peg, and this peg should be inserted in a hole. The hole typically has some chamfers, so this diagonal invitation sides, in order to ease the insertion even in the presence of a small lateral and angular clearance. So the robot is pushing down the end effector, its end effector, so including the RCC, the gripper, and the peg that should be inserted in the hole. So the assembly force on top represents this motion of the robot, which is planned independently of the presence of a contact or not. Now, if everything was perfectly known, so the geometry of the environment, so the position and orientation of the hole is known to the robot and the robot has very accurate positioning, this task could be performed in a pure geometric way. However, due to a number of uncertainty and disturbances, there could be a misalignment, both lateral of the peg with respect to the center of the hole, and also angular, so a cocking misalignment between the surface on which the hole is placed and the vertical direction, or the vertical direction of assembly. So a cocking misalignment. So while approaching first in free motion and then in the first contact, there will be a contact typically on one of the chamfer laterally to the hole. So if there's a large error, in fact, we are touching the surface completely out of the hole, and then the presence of RCC point would not help. So we are talking now of small misalignment error during an assembly task. So when this happens and the contact, a single point contact occurs at the remote center of compliance or very close to it, then the device, in particular the bottom plate, react by a small displacement exactly in the direction of the applied contact force. So the situation is the following. Since the first contact produces a force laterally, then the top plate, the bottom plate, is displaced in the same lateral direction with respect to the top plate. The robot continues to push exactly in the same way, so continue to lower down the whole set of devices which is mounted on the end effector, and this will sooner or later will bring the peg in double contact. So at this point, this double contact produces two contact forces which generates momentum on the peg hole, and therefore, since the peg hole is rigidly attached to the bottom plate, to the gripper, this moment will generate a rotation around the remote center of compliance point. And as you can see from this sequence, you will see that passively the hold peg will accommodate to the actual positional orientation of the hole. Indeed, this whole process will be successful only if we tolerate small uncertainty on this assembly task. These RCC devices have the possibility of adjusting offline, so not in real time, their center of compliance. And the actual position of the center of compliance may have a strong influence on the behavior of the bottom plate with respect to an assembly task. For instance, if the center of compliance is positioned by tuning the mechanical parameter of the RCC too high or too low, the reaction of the point of contact, at the point of contact, to forces or momentum will be not a pure translation in the direction of the applied force or a pure rotation around the contact point. All this will occur at the center of compliance. So only if the center of compliance is positioned close to the point where the contact will actually occur, so at the lower part of the peg being inserted in the hole, then a correct decoupling, mechanical decoupling of motion will occur. So the bottom plate of the RCC will react with a linear motion in the direction of the applied contact force, or with an angular motion around the axis of application of a momentum due to the contact, typically for double contact situation. And in this graph, You can see from a study of assembly forces the typical evolution of the force while getting in contact. So when you see below the peg hole entering in single contact point on the chamfer side of the hole, and while doing this, because of the assembly force being applied from above, the contact force will typically linearly increase over the depth insertion. So here this graph is not over time, but is with respect to how deep we are getting inside the hole. So the first point of contact is the zero level of insertion, and from there on we'll continue to push, so we apply more and more lateral force until this forces breaks the friction at the contact and the peg starts sliding on the chamfer. So when this happens, the contact forces is being reduced and is kept to a constant value while inserting. At a certain point, after this sliding phase, there will be a two-point contact force, a generation of momentum, so the contact force will be affected in a estimated circular way in this case, but this depends of course on the geometry and on other aspects. There's a function also of the angle of the chamfer, of the coefficient friction in the contact. The hole diameter plays another role, in particular the difference between the part diameter and the hole diameter, which is in fact the clearance in the pegging hole task. Okay, so this device, for many industrial applications where tolerance are present but the accuracy is, and the knowledge of the environment geometry is relatively high, so it's what we call a structured environment, this RCC is a successful choice. Indeed, when conditions change, when the type of task change and interaction should still allow to execute the task correctly, so controlling forces and having displacement in the right direction, then the active strategy of compliance, of course, lends itself to a more flexible solution. In this case, we have typically the use of a Forster sensor, like in this slide. So the robot is equipped with a Forster sensor. Again, the top plate of the force sensor is attached to the flange of the final flange of the robot. The bottom plate may hold a tool, like in the left picture, where a polishing tool is being used in order to do counterfoiling on a given workpiece, and applying enough forces normal to the surface so that the surface is being polished. You can see, for instance, in the two photos on the right hand side, the polishing of a wash stand or of a metallic cabinet. Indeed, in this case, the motion and the force will depend on the geometry of the environment, so some information should be known about the geometry of the workpiece, and the exchanged forces are being recorded in a frame which is close to the contact frame. In fact, is where the Forster sensor is being mounted. So between the force sensor and the tool center point, so the tip of the polishing tool, there are no degrees of freedom. So this can be considered as a rigid body, and we know already how to transform forces and moments evaluated around a frame which is attached to the sensor in forces at moment in a different point, which is related by a rotary translation. And this is true for a rigid body. So this is why the force sensor is being placed at the end of the kinematic chain. and so indirect contact through an object which is a rigid tool with the environment through which the tip of the tool is in contact. So this is one possibility, so contour following for some polishing operation. There's another interesting situation, again in assembly, where you have parts which should match one to each other. For instance, when you're mounting geared parts where the teeth should be engaged with teeth from another mechanical part. So again, this insertion requires the detection of contact forces which represent the fact that you are not oriented correctly in any direction with the holding parts with respect to the parts that is placed in the environment, and the two should be one inserted in the other. So you can process force information, so you can reason about sensory information in order to adjust little by little, I would say, the end effector position so to complete the insertion. So in this case, this is a form of active compliance, and there are ways in which you can process forces and generate displacement, or process displacement and generate forces according to an admittance or a compliance active control scheme. So these are two representative cases, but in fact there are many tasks in which environment interaction is of relevance. At the industrial level, there are a number of mechanical machining operation, like surface finishing or polishing we have seen before, and assembly, but also debarring, which involves the elimination of extra material, which is the result of some technological process made on the workpiece, and which is should be removed from the surface or from a contour of an object. For removing this extra material, we typically need to follow a nominal geometric path which is on the surface of the object while applying forces. Because if we don't apply forces, we are not able to remove this extra material, which is typically relatively hard. So this is an industrial application. There are other semi-industrial applications, for instance, in the radioactive environment, which are involved in nuclear plants, telemanipulation. In telemanipulation, we have a master driven by a human, and we have a robot slave which is reproducing through scaling and geometric transformation the motion of the master, and there is some remote contact, and this remote contact is fed back as a force sensation on the master and on the human that is moving the master. So this is what is called telemanipulation. So there is a remote contact, and this remote contact, the force in the remote contact is being transferred to the human operator, and this force feedback allows to complete telemanipulation task in a much more performant way. You can use also the contact, so the interaction with the environment, for instance, for exploring and identifying the shape of an object. Of course, you can combine vision information with force information, and you can start from an unknown object and do a contour following, and then create a 2D or even a 3D geometric shape of the object. So you're using actively the contact forces in order to understand the form, the shape of an object. We have seen such type of operation in one of the introductory video of this course. There are other more research-oriented situations in which environment interaction is of concern. For instance, if you have a dexterous robot hands, so a device with several fingers, I would say from 3 to 5, of the size of a human hand, more and more we are able to design compact hands which have the similar manipulability characteristic as the human hand. In these cases, we have contact in several points, and we would like to adapt the shape of the finger to the contact forces. We may have sensory devices distributed along the finger, along the fingers, not only at the fingertips, but also on each limb of a single finger. And so these multiple contacts will drive the way in which the hands perform, let's say, either a power grasp, so a grasp that resists to external forces, or fine in-hand manipulation, which require dexterity, and in this case the problem is much more harder. So, but in any case, this is a type of task where motion and force interaction with the held object is very important. And similarly, you may think of cooperation of multi-manipulator systems, so let's say 2 or 3 manipulators that cooperate at the same time holding a very heavy object, for instance, for serving a numerically controlled machine in which a single robot the payload would exceed, the weight of the payload would exceed the capability of a single robot. In this case, in the cooperation, small relative position error in executing trajectory will induce very large internal forces. So in this case, we should simultaneously control motion, but also the exchange of forces between one and another manipulator. And these are typically so-called internal forces, which may damage, in fact, the held object if not kept limited. And finally, the environment itself may be a human, one or more humans that are very dynamic environment in the sense that they apply forces, they move mostly in an unpredictable way or not known a priori. There could be cameras that overlook the motion of the human, and there are phases in which a physical interaction should occur. For instance, the human is passing object to the robot and vice versa, or together they're applying forces to a third object. So all this should be handled, and should be handled under an extra condition, which is full safety, because the human is now in contact or in very close proximity to the robot. So lightweight robots are being used in such situation, and this is a new trend in the Industry 4.0 and beyond of advanced automation. So even in this case, the exchanges of forces together with the coordinated motion are very important. So let's look at a little bit closer to some mechanical machining operation. Here in this picture you can see that there are multiple ways in which you can have a contact between a tool and a workpiece. And the workpiece may be stationary or may travel in different directions, while the tool may rotate or slide in different directions, and the relative tool workpiece motion is realized in different ways, and each is more appropriate to certain mechanical machining operation. For instance, here you can see a robot with a big tool mounted. This is an ABB motor holding a tool which is intended for abrasive finishing, so for removing rugosity from a surface by applying force. And here you can see two ways of holding the tool that may rotate in the first case around the horizontal axis, but this rotation internally to the tool will let the tool center point, so the point in contact, go in a alternative up and down direction, while in contact with the workpiece on which it's a force is being applied, and this force will execute the polishing task, in fact. There are other situations in which the tool holder apply directly rotational speed to the tool while in contact. So the normal force is still the force that achieves the abrasive finishing of surface, but the tool itself is rotating and not translating in contact with the environment or with the workpiece in this case. There are other ways in which you achieve abrasive finishing, so with the contact. For instance, in this small video, we will see a technological process in which, after having forged surfaces, there is a final finishing of the surfaces by a pneumatic machine, which applies what is called hammer peening. So it's a very high frequency oscillation in contact, so that it's like hammering at a very fast frequency, so that the resulting effect on the metallic part is that of an abrasive finishing. Let's see together the video. So you see that the tool is getting closer. Now it takes a reference, and now you see in slow motion or in fast motion the way in which the top of the tool, the tip of the tool, I would say, is going up and down on the surface and achieving removal of rugosity, so that these surfaces are very smooth. And here you can see that we may need the full degrees of freedom of the end effector of the robot in order to accommodate complex geometries, like in this case, where the hammer, the tip of the hammer, needs to follow curved surfaces, and also this is a close-up, and also in order to avoid collision should also reorient in the proper way. Here you see at the curve, and so on. So this gives an idea of the type of contact motion that is needed. In this case, this device by a company which is called Semantech, mounted on a ABB robot, is following the path while in fact applying forces. The fact that these are oscillatory forces is connected to the technological process itself. There are other ways in which this operation can be done, and you may be surprised, but you can do surface finishing also without having contact, so in which the forces are not of importance. For instance, in the top video, you see a technology based on fluid jet, in which high pressure liquid is being pushed against the surface. So what you see, the line that you see, is in fact is a high pressure water, or a mix of water and other components, by which you're soliciting this surface in the various directions in order to polish them. And you see that some water is coming out of the workpiece, and in fact this needs a lot of preparation of the environment in order to avoid to spill over everything. But this is a very successful technology. It has been used, for instance, in a European project that we participated up to 2 years ago, the Simplexity project of the H2020 program. Another technology which achieves surface finishing without contact is a laser technology. In this case, of course, the laser is mounted on the end effector of the robot. It's a high energy laser, but it's a pulsed laser. So In any case, the human should not be close to the system, and this is why this type of robotized surface finishing is realized inside a closed chamber, so in the absence of the human. And you see here the red dot is in fact the pulsed laser that is being applied to the surface of the object being carried. And the object then can be reoriented so that the processing can be made on different surfaces. And in this case, it is very clean and precise, of course, because there's no material or support fluid being used like in the previous case. So this is just to mention that there are other ways in which you can do this mechanical machining without the need of having contact. Of course, in this case, you need a high accuracy in position only. And this is the task is being completed, and the object is removed from the laser chamber. So, in all these cases that we have considered, so this physical interaction task, we have seen that in general there's a desired motion, so things should not be done necessarily in static positioning only. Even in assembly tasks where the speed involved are relatively slow, there is a motion involved in the operation, but together there are data collected and processed in order that some desired force is being also realized at the contact. So we have a hybrid situation, both at the planning and at the control level. So we should plan a task in which motion and forces are assigned, and of course, after having planned such task, we need to do control, which execute the hybrid control of both quantities in a suitable way. Now, in particular, there are situations in which we want explicitly control the contact forces, so we assign a value to these forces and torques, and we close a loop between the measured quantities and the desired quantities. So this is a conventional force control loop. There are other situations in which an exact value of force at the contact is not strictly necessary. The only thing we would like to do is to apply some force and to keep this force limited below a value which may damage the parts or the human on the other side. Okay, so this is a basic difference also in the way we model the interaction and in the way we process the data information in order to realize the proper interaction. We will see that there are situations in which the model itself is compliant, and there are situations in which the best model is a very stiff situation, so a purely geometric situation in which the end effector is constrained to live on a surface, and accordingly there are different ways from this modeling of processing the control law. I present here a bit of history from control approaches in the presence of interaction. These are very old works, but just to show that this problem was felt important right from the beginning of the robotic area. So between the late 70s and the mid of 80s, the foundation of interaction were laid down by a number of researchers, so I'm not reporting years or publication, but just the name because they were quite important in the history of robot interaction control. So David Whitney in the US started simply, he was interested in assembly, so in quasi-static operation, and there were during part insertion a number of deadlock that could occur while doing pure position control. So he proposed the explicit measurement of forces, either directly or indirectly, for instance, measuring the applied current to the motor of the system interacting with the environment, and of course when you are in contact and you try to apply a force, the current in the motors will increase, so by measuring the current you indirectly could measure the force. Or having a cell, a load cell, so a single degree of freedom device measuring force in one direction, to be included in the assembly operation. So he was the first pioneering the explicit control of force in assembly. Right after, there were different way of achieving admittance or compliance control. So Paul and Salisbury and Shimano wrote a number of papers and implemented system in which the contact forces were controlled by controlling position or velocity of the robot and effector. So you have a stiffness control or a damping control in the two cases. Or letting, so in this case you relate forces to motion, so you have an admittance control effect. Or you may react to displacement, generating forces by virtual spring and dampers in some selected direction or in all direction. In this case, from a deformation you generate a force, so you do what is called compliance control. Later on, Hogan, in a very important two-part paper, introduced the concept of impedance control, namely of design and control law. So we are talking in all cases of active compliant strategies, so software-based or control-based strategies, in which when the robot is in contact with the environment, we would like that the behavior matches some reference model in which forces and position dynamically interact, typically like a mass spring damper system. We can tune the parameter of the model in such a way that we achieve a good behavior at the contact, although we are not explicitly controlling, so setting references for forces, nor setting reference for position. In fact, it's a combination that occurs in this interaction. And this combination behaves like a model that we have chosen and which parameters can be set according to some intuitive physical reasoning. In fact, impedance control mimics, we will see a simple example, the behavior of a human hand, human arm, moving in an environment which is partly free space. Some area we may interact with a physical wall, and there is some uncertainty in this. So the best behavior that we apply is that of an impedance controller, and this has been replicated also on robotic arm. Finally, led by Mason and then by researchers like Rabert and Craig, and finally by Usama Khatib, there has been the concept of hybrid force motion control. So in this case, we start talking about so-called task space, which is a kind of a variation of the Cartesian space. So there's a new frame being defined and associated to each hybrid force motion control task. This task frame moves together with the execution of the task, and in this particular task frame, its position and orientation is such that in each of the individual directions we can either control force or control motion. By motion I intend position, velocity, whatever. And this type of decomposition of the Cartesian direction, in particular in the direction of the task frame associated to the task, is followed by a purely kinematic controller, so eventually we are specifying velocity command at the joint level, or by involving the full dynamic model of the robot, and this is the latest results by Khatib, which set a standard in this type of context. There has been many variations in the hybrid force motion control literature, in particular including deformation of the joints of the robot, or a model of the environment which includes further dynamic elements, and so on and so on. But basically, the layout was set by the work of Khatib. In fact, this work is the most appropriate for dealing with dynamic interaction when the motion needs to be accurate and relatively fast, and the forces need to be controlled as well. So, again, to summarize, the hybrid task in general require both reproduction of desired trajectory, low speed or high speed, we don't care in general, which are defined on the surface of object. So trajectory tracking, but in the presence of a contact. And as well, we would like to be able to control the exchange of forces and torques applied at the contact. And this independently of the fact that the environment has a soft or rigid characteristic, so low or high stiffness. You should think of the following aspect. Imagine that you have your hand moving in contact with a table. Now, if you observe this motion, you don't realize if you're moving, not immediately, if you're moving, if an external viewer is looking at you, he or she doesn't realize if you're moving the hand while applying force or just sliding in contact. Which means that if the interaction is through rigid contact, the difference in position between no application of force or high application of high force is indistinguishable. So in this sense, you need an extra sensor which allows you to estimate this contact force. This is a very important point. So really, there are tasks in which position control cannot do the job. There are other situations, especially when the environment is relatively soft, in which you don't need to control force, and you may interact with the environment without having an explicit force control. So here in a debarring task, for instance, so when you have to remove some extra material from a surface, and now I'm not considering the metallic surface, but I'm considering, for instance, in this picture, removing of extra plastic material or glue from the border of a windshield of a car, or when the robot is performing another paradigmatic task, which is turning of a crank. For instance, this is models the situation when the robot needs to open a door, for instance, in a domestic environment. This operation is similarly to a phase of turning the crank. Then in these cases, exactly, you have to follow trajectories, otherwise you, for instance, in the second case, you will induce a very high internal force, and you may crash, for instance, the handle of a door. So accurate execution of trajectory, but together explicit control of forces. So exactly the interaction task of our interest. Now, talking about the debarring task, here I have a picture taken from a master thesis performed many years ago in an ABB Excellence Center in the vicinity of Rome. Unfortunately, this center has closed, so we cannot cooperate with them anymore, in which there was an industrial ABB mounting an extra tool, quite heavy tool, you see also with the connection cable, which was a pneumatic tool holding a blade with 1 degree of freedom and a load cell measuring the contact force. So the idea was the following. You see on the support plate a car windshield which has been produced, but whose border needs to be refined, so you need to deburr materials from that before the windshield is being assembled in the car body. So this task is executed by letting the robot program in such a way that it follows the nominal geometric path along the surface of the windshield, and at the same time apply a force through the pneumatic piston in the tool and reacting to forces by having some compliance at the contact. In fact, this system was a two-blade system. The first blade was controlled under force control, so some force need to be applied, otherwise this material, which is relatively stiff once it comes at ambient temperature, so you need to apply a certain force in order to remove this extra material. So there was a first blade controlled in force, there's a second blade coming after, just pushed by a passive spring, which removes the remaining extra material. It's like the two-blade system which was made famous by Gillette. So there are other aspects in this situation, because you can imagine that while following the four sides of this car windshield, first of all, the windshield has a curved surface. So these are not straight paths, they are curved paths. Second, when you're removing parts below on the side, which is on the downside of the windshield, of course gravity will act against contact. So the weight of the tool itself will tend to detach the blade from the surface. So you have to compensate for gravity. Similarly, when you're going above and you're pushing in the down direction, gravity will help in this. So regulating force makes sure that any uncertainty in gravity compensation is, let's say, taken care of by the force control loop. So we may be a bit farther away from where we should be or closer. In any case, it's the force error that will regulate our position, independently of these external disturbances, including non-perfectly compensated gravity. Okay, so as I mentioned at the beginning of this introductory lecture on interaction, robot interaction with the environment, we typically design the control based on how we model the environment. Okay, so the environment model which is more appropriate suggests also the more appropriate control scheme. Now, by and large, apart from simplification and special cases, there are two classes that we will consider: impedance control and hybrid force motion control. So these controllers are motivated by the way in which we model the environment. So in the first case, we assume that the environment is a mechanical system, but this mechanical system is not infinitely stiff, so it undergoes small but finite deformation when we push on it. Okay? So when this is the case, if we have a robot in contact with such a compliant element, a compliant environment in a sense, then the forces that will arise will be a balance between two dynamic systems. On one side the environment, on the other side the robot interact. So forces may be due, large forces may be due because the robot is relatively stiff or the environment undergoes finite deformation, but these are very small, so we are getting toward a fully rigid environment. So depending on the coupled two dynamic system, the forces will arise accordingly. So when impedance control does the following: assign to this interaction not the characteristic of a model to be matched. So not regulating exactly the force, and sometimes not even having a reference for the force, so keeping forces limited, this is the typical case, and not regulating position, because if we assign a position, a desired position which is inside the environment, then we are not guaranteed that we will be able to zero the position error, unless we tolerate very large contact forces, which is not what we are intended to. So there will be a compromise in the choice of the model in the presence of a compliant environment. So a mechanical system that undergoes some form of deformation. On the other hand, hybrid force motion control is most suited if the model of the environment assumes high stiffness or infinite stiffness, which means that the environment is fully rigid. So when the environment is fully rigid and the robot approaches this environment, and from one instant on it should keep contact in order to execute this, for instance, mechanically finishing task, then this rigid environment provides a constraint when the robot is in contact. In fact, it's a unilateral constraint because the robot can enter in contact but can always leave the contact, so retracting itself. It cannot go inside the object. However, as long as we are interested in controlling forces, we should keep contact. So this unilaterality can be considered as a bilateral constraint. So like having the robot being glued on the, or the end effector, or the tool of the robot being glued on this geometric surface. So you can imagine that the contact forces in this picture result from any attempt to violate the geometric constraint. And in fact, this is a way in which such kind of very relevant situation can be modeled, and accordingly you can define the composition in the task space of direction where you satisfy automatically the geometric constraint, so free motion direction, and then you would like to control the way in which you move along this free motion direction, and other direction where you cannot violate constraint, but while attempting to violate, you generate reaction forces from the stiff environment, and of course you would like to control these forces. So you see that the picture, the two approaches are kind of complementary. There are pros and cons on both situations, but essentially are driven by the type of model which is more appropriate to describe the interaction with the environment. I should mention two additional aspects which are very general at this stage. There has been a long discussion among robotics researchers about which of these two approaches is better. And this, in my view, makes little sense. The group of people that sustain impedance control mention explicitly the fact that in impedance control you don't need an accurate level of knowledge about the geometry of the environment. Instead, in hybrid force motion control, because you're writing down geometric constraints, so you need to know exactly this geometry, and this may become a restrictive requirement. But in fact, this difference is only apparent, because if you want to if you look at the performance becomes similar with a similar amount of knowledge about the environment. And we will comment on this while dealing with impedance control or with hybrid force motion control. So this level of knowledge is kind of similar if you would like to achieve good performance in the interaction. I must say, however, that while in the hybrid force motion control, you need to measure forces because you close the loop around the force error in some direction. So you need to have a measure of force. Now, this measure may be induced by some model-based virtual sensing, but this is a different story. You need a measure of force. On the other hand, in impedance control, you may need force measurement, but if you release the performance in particular, if you accept to live with the actual inertia of the robot at the contact point, we will be more clear later on this aspect, then measuring contact forces is not strictly needed. Okay, so this is essentially a true difference between the two approaches. So let me conclude by showing a number of examples where the environment itself lends itself to a model which leads to impedance control or to a rigid model which leads to hybrid force motion control. So first of all, two videos in which impedance control has been realized on one case, or hybrid force position control has been realized in the other case. In the first case, you can see a mobile manipulator, so a research manipulator mounted on a mobile platform, navigating in an indoor office environment, and approaching contact with a door, in particular with the handle of a door, and needing to open the door by acting on the handle. So this situation is a typical situation in which impedance control works fine. Why? Because you don't need really to assign a force in the contact. You should need to establish contact and then interact so that you can move the handle in some direction. And of course, you can apply also forces which result in reaction forces as long as these are limited. And then you progress with the arm and the base, so this is a complete system, in order to open the door. In the right video is a more fancy situation in which there's a robot holding a piston and needing to insert the piston into a motor block. Now, to make things more complex, the motor block is not static, but is moving, rotating on a turntable. So the robot is equipped with a force torque sensor and with a vision camera. So it recognizes the geometry of the holes. So this is a peg-in-hole task. Once it reached the same speed of the rotating turntable, so that the image is fixed in the field of view of the camera mounted on the end effector, then so you have, in a sense, located the position of one of the motor holes. Then you proceed in getting contact, and when you're in contact, the piston with the motor, you process force information in order to adjust and do the insertion like you have seen in this video. Okay, so as I promised, I would like to make some schematic example of the two situations. So the typical situation where you can assume a geometric constraint being imposed to the robot end effector, and this of course will limit the full mobility of the end effector, but on the other hand will allow the end effector to apply forces to the environment. Is when you have a work workpiece, a rigid workpiece, with a rigid tool and essentially a rigid full structure of the system. So robot, wrist, an RCC or a force torque sensor, or in some cases both of them, and a tool which is in continuous contact with the workpiece. Then, in this case, we would like to have a stable contact, and this is not so easy as one can imagine, because there are situations in which, in the attempt of controlling the force along a certain direction, there could be some chattering phenomena, which is a way of revealing some instability in the control design. So we would like to have a stable and accurate following of the geometric surface, and this is because the workpiece is very stiff and the whole system is very stiff. So we would like also to apply a desired contact forces. So this is a typical situation in which a constrained geometric model works at best, and therefore a hybrid force motion control scheme. Well, this is another compliance situation, I would say a rather unusual one. This picture and the sketch comes from a work that has been performed over decades now in Australia for ship shearing. In fact, as you know, there are nowadays, I think this is still true, more ships than humans, so the activity of ship shearing is one that you would like to automatize in this situation. So the ships are being, this is a prototype that we have done a number of improvements lately, but the idea that I want to convey is the following. So the ship is being held in place, and there's a complex multi-degree of freedom arm mounted on a trail, on a linear trail, that carries a ship's shearing tool. And of course, the geometry of the ship is uncertain. You could have a bigger one, a smaller one. So you have an approximate model to work with, an approximate geometry. So you need to enter in contact. Indeed, if you don't push enough, you will not be able to cut the wool. So remove the wool from the surface of the ship. However, if you go too down and you assume that the ship was smaller than expected, so your geometric model is very bad, you may even kill the ship. So this is a typical situation in which you like to keep forces limited. You don't really need to follow a trajectory, so you need to interact in a compliant way, so with an impedance model, which is most appropriate for performing the task. So the quality of the results is being able to shear the wool of the ship. Now, this, as I said, has been improved over the years, and remains a question if the ship is happy with this type of automatic treatment, but this is a different story. And finally, there are indeed also situations where a mixed condition applied. So the interaction may occur at some times with a geometric and rigid environment, in some other situation or phases of the task, a compliant treatment would be better. So for instance, in this case you can see a phase of assembly in which there is an approach phase, free motion, there's a first contact, and this is a hard contact with the surface, and in this phase searching for the hole, so we are assuming that we have a large uncertainty in this pegging hole assembly task. So in this searching phase we are in contact, but we can assume a geometric surface or a rigid surface until we get close to the hole, and the third phase, the insertion phase, can be performed either with a RCC, so in a passive way, or in an active way, but assuming some compliance in the structure, in particular in the presence of an RCC, which is per se a compliant element. Remember that compliance can be distributed in several places, not only at the contact, there could be compliance also at the joints, if we have elastic joints, and all this type of compliance contribute to the actual interaction, and we will see more as we proceed in the analysis. So for the time being we stop here. The next lecture will be devoted to ways of handling geometric interaction, so situation in which the contact is stiff enough. And we will see this with simple cases first, and then detail the general formalism of modeling and control. Thank you for listening for the moment.